remember the truncated SVD, where the aim was to get the condition number a lot smaller by changing your operator only a little bit. And the condition number, being a product of norm A and norm of the inverse or pseudo-inverse of A, can only be changed in the second factor, really, if you want to change A only a little bit, because by changing your operator only a little bit, the first factor will not change enough. So the key question was, can we, or how can we get the norm of the pseudo-inverse below a given bound, something like 10, by changing the operator A only a little bit or as little as possible. And the key was to play around with singular values. We identified the small positive singular values being the ones that are responsible for a large norm of the pseudo-inverse. And if we move them into 0, then they don't hurt anymore. And the change was still little because we are only changing the little singular values. So in the end, we can achieve a pseudo-inverse less than 10 by changing your operator by only a tenth. Okay, and similarly, you can get the condition number below a given bound by changing the operator by norm A divided by 10. Now we come to an alternative approach to regularization, which is probably more famous, or the most famous kind of regularization, so-called Tichonov regularization, section 4.6. And as usual, we are given an operator A and the right-hand side B, and like last time, the condition number of the operator is large. And still, as usual, the aim is to solve the equation AX equals B for the unknown X. And like we just recalled, the other regularization technique, the TSVD, had two goals. We wanted to change the operator A, so in some sense the problem, only a little bit, in order to get the norm of the solution operator, which is usually the inverse of A, or more generally the pseudo-inverse of A, below a given bound, like 10, and thereby make the condition number small. But now here is Tichonov regularization, which is an alternative technique, but with two very similar goals. Find an element X in your first space X, so-called Tichonov solution, such that you get a good compromise. On the one hand, you want to solve AX equals B as good as possible in some sense, so you want the error to be small, and at the same time the norm of X, which is the Tichonov solution, also to be small. Now, how is that similar to the TSVD? Well, in the TSVD we change the operator a little bit and then solve by least squares, because the new operator has 0 singular values, you cannot solve exactly anymore. But solving by least squares means you're looking for a small solution or a vector with a small norm for which the error AX minus B is minimized. That's almost what we say here. And then the second wish in the TSVD was to get the norm of the solution operator below a given bound. Well, the solution operator is the operator that takes your right-hand side B, which was given, to the solution X. And aiming for a small norm in your solution operator means aiming for a small norm in your solution. So it's indeed quite similar. We still have to express how these two wishes, 1 and 2, which are often contrary to one another, will be combined in the Tichonov regularization. But before we do so, let me introduce you to Mr. Andrei Nikolaevich Tichonov, a Russian mathematician and geophysicist in the 20th century. And you will find his name in lots of different spellings here and therefore also here. And of course the only proper way to spell his name is this, with a little emphasis on the E. Okay, we just said it. The two conditions 1 and 2 in blue also lead to the least squares solution, and hence to the definition of the Moore-Penrose pseudo-inverse, where first of all you minimize the error, and then, and only among the minimizers of 1, you take the minimum of the norm of the solutions x of problem 1. Okay, well, we know this. This two-step minimization process here takes you to the least squares solution, little x. Now, in contrast, Tichonov is combining the same two wishes 1 and 2 a little bit differently. Tichonov avoids this two-step minimization by just combining wishes 1 and 2 in a sum with a little weight in front of the second wish that is telling you how important the second wish is compared to the first, and then just performing one minimization step. And just like in this whole least squares scenario, the theory becomes a lot nicer if you put squares here, and if you do that, then why not here? Okay, so that's the idea. Now let's try to implement it. So you define this new function f of your element x as the error that comes from wish number 1 squared plus lambda squared times norm of x, which comes from wish number 2 squared, where lambda is sometimes called coupling parameter. It's just telling you how important is wish 2 compared to wish 1. Okay, and again, why are we putting squares here and here? Well, essentially because we want to combine these two norms here into one new norm that should give us a Hilbert space structure. So we want orthogonality, we want the fact that minimization has something to do with orthogonality, and we know that if you want a Hilbert space, you need squares. Okay, and now that we said it, it's actually not too difficult to interpret the sum of squares as a new norm of something. And here's that something. So you're essentially taking two vectors, even though they might be infinite dimensional objects, and you're combining them into one vector in terms of Cartesian product. So you just take an ordered pair of two things, and you equip it with a new norm by saying, well, just like you would usually compute the Euclidean norm, you take the size or the norm of the first object squared plus the size or the norm of the second object squared, and of course that gives you exactly what you get here, and that is the norm squared of your new object. And you can see that obviously we're thinking in terms of Euclidean norms, of two norms here. And of course you will say that little lambda is coming out as modulus lambda of the norm. So we should put modulus here, but on the other hand we're putting square, so modulus is not so important. But of course our weights will always be non-negative, or let's say positive. So we keep at least a little bit of wish number 2 alive by imposing lambda to be non-zero. Okay, and now how do we proceed from here? Well, let's split this vector here into a part that has x and another part that doesn't have x. And then rewrite this first vector as an operator applied to little x. where we have to interpret this here as an operator that is acting on this Cartesian product. So this is acting on the first component, and that is acting by multiplication by lambda on the second component. Okay, and now this should be minimized. And this is essentially where the Hilbert space argument comes in. You say that you're minimizing a distance, which is the distance of this element operator applied to little x, from this right hand side, which is combined from our old right hand side b and 0, by looking for a point x where this result here, this output connected to the right hand side, is orthogonal to the space of all outputs, which is the image of this operator. And this is exactly what you do in least squares problems. So you can roll it all back to the approximation theorem, which says minimization happens if and only if something is orthogonal. Or you just call it the normal equation, which is what you do in least squares problems. And to write that normal equation down, let me just relabel this operator as b and this right hand side as c, and then your normal equation is b star times bx and now equals b star c. Remember, this equality here is equivalent to x solving the least squares problem. Bx is approximately equal to c. Okay, now we can rewrite everything in terms of a and lambda. And now note that you're working with the adjoint of this combined operator here, just like this was a matrix with, well, simple entries. So you're taking the transpose and then you're taking the adjoint in every component. And actually you would have to take complex conjugates here for lambda. But of course, lambda being real, this is not necessary. And now you continue to work with these products here, just like if you have matrices. I mean, essentially, this combined operator B is a matrix with two operator entries. So you're perfectly fine working with it like it was a matrix. So you just multiply here, and you multiply here. And now remember, we want to solve for x here. And we are very close to the solution. We just have to get this operator out of the way here. So let's keep fingers crossed and just take the inverse and bring it to the other side. And there's your solution. Well, okay, we should discuss the last step. I mean, why can we invert this operator? Why does it have an inverse? Okay, remember A star A. So when A is invertible, then this is always positive definite. We did this in section 3.7 on positive definiteness and rectangular finite sections. Now in general, A will not be invertible, but even then this is still positive semi-definite, which means its spectrum is real and non-negative, but possibly containing 0. So this operator might be non-invertible. Okay, but now comes plus lambda squared I. And this means every spectral value moves by lambda squared to the right. So that the whole spectrum is moved away from 0 by lambda squared, which is non-zero. It's positive. So in particular, 0 is no longer in the spectrum, and that means indeed this operator is invertible. So we can happily write down the inverse here, and we arrive at the solution operator for the Tichonov regularization problem. And similarly to the TSVD operator, let's label it by R as in regularization, Tichonov of A, and of course we also have to write down the parameter little lambda. Okay, excellent. Let me make two final comments before we close this section. First comment. We mentioned from the beginning that the same two conditions 1 and 2 are also used to define the more Penrose pseudo-inverse, just in a slightly different combination, as a two-step minimization rather than this one-step minimization using the coupling parameter lambda. Indeed, one can recover the more Penrose pseudo-inverse from our Tichonov solution operators. One can indeed show that the limit of this operator expression here as lambda goes to 0 is just the more Penrose pseudo-inverse, and that is true at least for finite matrices. And of course we know that the limit as lambda goes to 0 is in general not the same as just plugging lambda equal to 0 into that formula. Well, first we didn't even allow lambda equal to 0, and then if we try we get the following, where obviously we can drop this 0 operator here, and we can also interpret that operator as follows. It's the solution operator for this problem here. So if this is uniquely solvable, then you have an invertible A star A, you just bring it to the other side, and then X is given by this inverse here applied to A star applied to B. Okay, but that is just the normal equation for AX approximately equals B. So indeed you get the more Penrose pseudo-inverse, but of course you can only plug in 0 if you can evaluate that expression here, that inverse. So you can only do that if A star A is invertible. And this, one can show, is equivalent to A being bounded from below. And remember, this means that A is injective and has a closed image. Of course, all of that is true if A is invertible. Well, in that case, the pseudo-inverse is just the inverse, and you can see that directly because the inverse of this product is then just the product of the inverses, and then you get A inverse times A star inverse, but that hits A star and you are left with A inverse. Okay, the second comment that I wanted to make was that one can arrive at the Tichonov regularization formula via a completely different approach. Well, it's actually not completely different, it's just an alternative way to implement your two wishes 1 and 2. Remember that we want to minimize the error or keep the error as small as possible, and at the same time keep the norm of the solution small. And another way to start this is the following. Well, at first you specify an upper bound, let's call it capital M, on your norm of x. And then you minimize your error term, but under the additional condition that you're only looking for solutions x which have a norm less than or equal to m. Now obviously the meaning of this minimization doesn't change if we put a square here, and the meaning of this inequality doesn't change if we put squares here and here. And then you can attack this constraint minimization problem via Lagrange multipliers. So you define your Lagrange functional, let's say L of x and mu, as, well, you start with your cost function or your function that you want to minimize, and then you add, well, multiplied by the so-called Lagrange multiplier mu, your inequality condition, where you rearrange your condition so that you get an inequality less than or equal to 0. Okay, and then in your Lagrange method you would compute the gradient of that L function and put that to 0. But the partial derivative after mu would just give you your side condition here. And okay, well, putting the gradient after x, or in all the x directions, down to 0, we could just say we are minimizing the whole thing as a function of x, and we are treating mu as a parameter here. But if you do that, you will spot that this term here doesn't even contain x, so it is constant, so you can just drop it when you're looking for the minimizer little x, and all you're left with is your Tichonov ansatz.